This lecture will focus on better understanding free energy of reaction, that is delta G, and we'll be focusing on this particular formula involving delta G, which tells us that free energy depends both on enthalpy of a process or reaction and entropy. Just a quick reminder of what free energy is. It is the energy available to do work. It's the useful energy. Energy, one way to classify it is either thermal energy, which we call entropy, thermal energy, which we call enthalpy, and entropy. We have also learned that energy may start in a very concentrated fashion, but then as it's either transferred or transformed, it spreads out due to entropy. So we kind of do that to show that it's spreading out due to entropy. And so the energy that we're left with after we've transformed it into another type of energy or used it is less useful. Again, as a reminder, I like to look at this free energy equation from a mathematic point of view. If enthalpy is negative, and remember that means the process is exothermic and it's favorable, and if the entropy is also favorable, in other words, if entropy is increasing, then if you simply look at the math of this equation, delta G under these conditions will always be negative, and therefore this will always be a spontaneous process. Looking at it from the other point of view, or the opposite point of view, if enthalpy is unfavorable, in other words, if it has a positive sign, which means an endothermic process, and at the same time in this particular process, if entropy is also unfavorable, if entropy is decreasing, and therefore has a negative sign, if you simply look at the math of this, you end up with plus two negatives, give you a plus. So overall, delta G, or the free energy of this process, will always be positive. Therefore, it will always be non-spontaneous, right? We're going to be doing quite a few calculations for free energy, and it's just a good idea to know what you expect, whether you expect the answer to be positive, negative, spontaneous, or not. All right, so the tricky part of predicting what free energy is going to be for a process is if enthalpy and entropy are opposing one another. In other words, well, that'll be the case if they both have the same sign. So let me explain that a little further. If enthalpy is negative, we're just going to look at this from a mathematical point of view, and entropy is negative, okay? So that means that enthalpy is exothermic, it's favorable, and entropy is unfavorable, okay? So if one's favorable and one's unfavorable, what's the overall process going to be? And what does it depend on? Well, in these cases where one is favorable and one's unfavorable, the delta G value depends on temperature, okay? So let's look at the case where they're both negative. Remember that we want delta G to be negative in order to have a spontaneous process, which means we want to emphasize, or we want the enthalpy term in this case to predominate because it has a negative value. We want to minimize the entropy term because delta S is negative, right, which is unfavorable, and of course two negatives make a positive. So we want to minimize that whole term. How do we minimize this whole term? Okay, we do so by lowering the temperature, right? So notice here, if both enthalpy and entropy are negative, then low temperatures will favor a spontaneous process. High temperatures, the entropy will predominate, and since it's not favorable, it will be non-spontaneous. Let's look at it now for the situation when both enthalpy and entropy are positive. Okay, I'll just put that in there. There you go. All right, so again, remember, in order for it to be a spontaneous process, delta G has to be negative, okay? So purely mathematically speaking, we would like to minimize the delta H term, or we'd like to maximize the T delta S term in this case because there's a negative sign there, okay? Remember, delta S is positive. So overall, there's a negative sign. How do we maximize this whole term? We do it by using high temperatures, okay? So whatever term is favorable in the equation, if they're opposing each other, whatever term is favorable is the one that you want to predominate. And the only control you have over this equation is by temperature. Okay? So this chart is a nice way to summarize it. Not only do you need to have this chart memorized, you need to be able to explain why the spontaneity is what it is. Here's just another way of presenting the same information that may appeal to you more. So these are the situations where delta G is spontaneous, okay? It is always spontaneous when enthalpy is negative and entropy is positive. Remember, those are the two favorable situations. It is always non-spontaneous when enthalpy is positive. That's an endothermic process. And entropy is decreasing. Both of those are unfavorable, so the process overall will be non-spontaneous under all conditions. These are the two conditions that you need to better understand and be able to explain. If you have, for example, entropy that is favorable, that's positive, but your enthalpy is also positive, which means it's endothermic and not favorable, then the process will be spontaneous only at high temps. If enthalpy is favorable, exothermic, negative, but entropy is also negative, which is unfavorable, the process will be spontaneous only at low temperatures. All right, so take some time to make sure you understand those. Here's kind of a little test for yourself. So this is the point at which I would say, I would pause the video and see how you would answer these two questions on your own, and then I'll explain them in a minute. So this question, let's do the one down here first, is asking you to look at this image. And I will tell you right now, this curriculum uses a ton of pictorials. And so it's really important that you understand how to interpret them and sometimes even draw them. And so the reason we do that is because to really understand chemistry, you need to understand it on a particulate level, on a molecular level. And so assuming these little green balls are particles, molecules, what's happening in this process? If somebody asked me to explain, I said, okay, it looks to me like it's going from a solid to a gas, okay? So, assuming that's the case, what has to happen in order for that process to happen as far as temperature? Would you have to increase temperature? Would you have to decrease temperature? Or what? Well, I'm hoping all of you know that to go from a solid to a gas, okay, or liquid to a gas, or solid to liquid even, that you need to apply some type of energy. And so temperature would be just thermal energy. So the correct answer is increased temperature. All right, so keep that in mind because remember our equation for estimating free energy, it's got temperature in it. So you really always need to be aware of temperature. I also want you to kind of tuck make a note of or tuck back that temperature in this equation must be in Kelvin. All right, this is the more important question at this point. For this process, what is the sign for enthalpy, entropy, and delta G? So let's take them one at a time. Enthalpy, heat energy, thermal energy. When something goes from a solid to a gas, what is the change in enthalpy? Okay, in other words, when it's talking about enthalpy, it's asking you, is this an exothermic process or an endothermic process? Well, if it is going from a solid to a gas, that is called subliming. But regardless of what exactly it's doing, it's going to a more free state, and that is always an endothermic process. Okay, so melting, subliming, vaporizing, all of those are endothermic. Okay, what sign does an endothermic process have in thermochemistry? Okay? It has a positive sign. Enthalpy is increasing. Okay, this gas has a higher energy content because we've used a higher temperature than the solid. All right, entropy. I bet maybe that's easier to predict for you. What's the change in entropy for this process? And remember to think of entropy as freedom of motion. Okay, so is the freedom of motion of this system greater or less when it's in the gas state? I'm hoping you realize that freedom of motion is greater, and therefore the change in entropy is also positive. Now, here's the tricky part. So really, if you haven't turned off the video yet, I hope you do it now. Keeping in mind that the change in enthalpy is positive and the change in entropy is positive, what's the sign for delta G? See, pretend like this is a little quiz or test question. See how you would answer it. Well, if we look at our handy-dandy equation, okay, and put the signs in, okay, enthalpy is positive. I'll leave that negative sign in there. And entropy is also positive. So positive entropy is favorable, but positive enthalpy is unfavorable. They're playing tug of war. Which one's going to win? What does it depend on? It's going to depend on temperature, okay? And so what type of temperature is going to favor spontaneous processes? In other words, when delta G is, under what conditions will delta G be negative or spontaneous? We want to emphasize the favorable term in the equation. Entropy is the favorable term. We want to emphasize it, which means we want a higher temperature. All right, here's another practice for you. And these practices are really important to better understand this. So look at this process and predict what you think the signs delta S and delta H will be. So I'm going to give you a couple of hints. Just turn off the video right now if you don't need them. What exactly has happened here? I'm going to draw this out for you. So you have two of these, nitrogen dioxide, that are basically coming together. Okay, they're making a bond together to form N2O4. So that's what's happening chemically. So now, again, see if you can turn off the video and predict, and I'm going to walk you through what's going on here. Entropy. The easiest way to think of entropy is freedom of motion. What has more freedom of motion? Two separate molecules or those two molecules which are now bonded together? Okay? Which one of these scenarios has more freedom of motion? I'm hoping you can realize it's the two separate molecules. Once you make an extra bond, you've restricted the freedom of motion. Okay, so this has restricted motion, therefore entropy is decreasing and it's a negative sign. Well, you might ask yourself, how the heck am I supposed to know about enthalpy? I don't know anything here. What have we done? We've only made one bond. this is what I'm getting ready to say is critical for the remainder of chemistry. You need to have the understanding nailed to your long-term memory. Okay, so making bonds always 100% of the time are exothermic. Okay, favorable in nature. That's why so many bonds are made. Always exothermic. And exothermic processes have a negative delta H sign. All right. So delta S is negative and delta H is also negative for this process. Now, if you remember our table and looking at our formula, what happens when they're both negative? Remember, when they both have the same sign, it's going to depend on temperature, whether or not it's spontaneous. So if they're both negative, which of these two terms do you want to dominate, the enthalpy term or the entropy term? You want the one to dominate that's favorable. Exothermic is favorable, so we want to minimize the entropy term. And how do we do that? By lowering temperature. Okay, that minimizes this term. All right, so you will need to be able to actually calculate these values, the delta G values. So let's practice with that a little bit too. Okay, these are really all have the little degree sign, which simply means standard conditions. That'll be important down the line too. What do we mean by standard conditions? Well, the important thing to remember here is that temperature, understand the conditions, that's room temperatures, 25 degrees Celsius, which equals 298 Kelvin. All right, so go ahead and make sure you can calculate delta G under standard conditions for this process. The values are given here. I will caution you to be very careful of units. Entropy, since it overall is typically smaller than enthalpy, is usually in terms of joules, whereas enthalpy is usually given in terms of kilojoules. The units must match before you put them into the free energy equation. So go ahead and go through the process and make sure that you can get the correct value, which is minus 4.8. To remind you of the conversion factor from joules to kilojoules, if the problem asks you to give your answer in kilojoules, you're going to want to convert the joules for entropy into kilojoules. So we'll just do some dimensional analysis. The conversion factor is there are 1,000 joules in 1 kilojoule. Okay. So it would just be minus 175.8 divided by 1,000. So now that you know the value for delta G, at this temperature anyway, it's negative 4.8, is this process spontaneous under these conditions at 298 Kelvin? Well, hopefully you know to say yes. Anytime delta G has a negative value, it is spontaneous. And so just as kind of a side note, this is interesting. This looks like smog, right? It is. Okay. It turns out, we're not going to go into equilibrium till later, but it turns out that this particular reaction is reversible. It goes in the forward and reverse direction. And NO2 is brown colored, N2O4 is clear. But under high temps, the NO2 is favorable and NO2 is brown. So in the hot temps of summer, at least in the cities where you have a lot of these gases around, that's why the sky looks brown and gross. All right, just to get you used to some of the jargon, as I said, the reaction is spontaneous at 298 Kelvin. And we say this reaction is enthalpy driven. In other words, that tells you that the delta H enthalpy term is favorable, that that's what's driving the reaction to occur. So see over here, enthalpy is favorable, it's exothermic. Entropy is not favorable for this process, okay? It's negative. We want entropy to be positive, to be favorable. And so entropy is actually hindering the spontaneity. All right, so I kind of gave you the answer already, but I would see if you can answer this yourself. Okay, just kind of reminding you the signs we've established for the variables. What would you do to make the reaction in this direction more spontaneous? Okay, more favorable or more spontaneous means you want to make delta G more negative. So what would we do, what could we do to temperature to make delta G more negative? Look at the signs down here, okay? Delta H is already negative, so we want to leave this term alone. Well, we can't do anything to that term anyway, but we want to minimize the entropy term, right? It's unfavorable to begin with. Mathematically speaking, two negatives make a positive. We want to make this term as small as possible because it's hurting things. How do we do that? By using a lower temperature. Okay? So lower temperatures will favor the reaction moving in this direction. And that's why in the fall and winter you rarely, if ever, see smog because the N2O4 product is favored under low temps. All right, so I mentioned before that molecular level diagrams are important to interpret, and so are graphs. So this is a graph of free energy. Notice it's not delta G, it's just G, it's free energy. It's not change in free energy. So looking at this graph of free energy, for, we'll just say reaction progress down here. If you haven't already noticed, RxN is reaction. All right, so to get the change in any type of curve or line, you're going to do okay, so delta G would be picking two spots on the y-axis, right, since G's on the y-axis, and then calculate what is the change in G. If you are moving in this direction, so if you're moving from reactants to products, you're moving in that direction, according to this graph, it is going to be a spontaneous condition or spontaneous process because delta G will be negative, right? It's lower. So if you start up here, you have one G value, and down here you're going to have a lower G value, right? And so delta G is going to be decreasing, and so it'll have a negative value. So anytime if one of these curves for free energy, anytime you're going in the direction that takes you to a lower delta G, it's going to be spontaneous. Anytime you're going in the opposite direction, that you're going uphill, okay, so anytime you're going uphill, you're going from a lower free energy value to a higher, that would be a non-spontaneous process. So again, going in this direction uphill would be non-spontaneous, always. What's going on here? Right at the bottom of the hill. All right, so this is an important thing to get again. If you were at the bottom of the hill for free energy, that means the change in free energy is zero. Delta G is zero, okay? And because you're at a flat line, right? So delta G is going to stay the same here. It's not going to go up or down. When delta G is zero, the reaction is at equilibrium. That will be really important later on, so it's good to understand that now. A system at equilibrium has no driving force to do anything, okay? It's at the lowest possible energy state, so you are not going to have a spontaneous process at equilibrium. It's not going to want to do anything, okay? Alrighty. Here is another question. This is a tricky question. I always say I kind of rate difficulty of sample problems from 1 to 5, 1 being the easiest, 5 being the hardest. This is probably a level 4, okay? This trips students up. Let's look at the equation for change in free energy. And we know, what do we know from the previous pages? We're still talking about the same process. So we know that delta H is negative. It's a favorable process. And we know that delta S is also negative, which is unfavorable. Okay, and we also know, since we want to minimize this term, that we want low temps for the reaction to be spontaneous, or delta G to be negative. So what if I were to ask you, all right, low temps, how low? Well, how low does the temperature have to be for it to flip over to spontaneous? How would you solve that? Well, remember I said at equilibrium. This is really important, by the way, so you might want to wait and listen to the slide till you're really awake and can focus. At equilibrium, right, delta G is 0, okay? We're down at the bottom of that curve, and there's no driving force at all. And equilibrium is the point at which a reaction will flip from being spontaneous to non-spontaneous. Okay, so think about it. If you have your delta G curve, it is spontaneous going downhill. Here's equilibrium, and it's non-spontaneous going uphill. So the equilibrium position, when delta G equals 0, is the point at which a reaction flips from spontaneous to non-spontaneous. So with that in mind, you want to set delta G equal to 0. What happens when you do so? You can rearrange the equation and get that delta H equals T delta S. Very important equation. Okay, delta H equals T delta S. So now you can solve for temperature. You can rearrange that one more and say that temperature, when delta G equals 0, would be equal to change in entropy over change in, I always do that, enthalpy over change in entropy. Okay, so that becomes easy as long as you know how to do it. And so let's go ahead and do that. Make sure they're in the same units and that you have your signs correct. The change in enthalpy that we found earlier in terms of joules, 50 minus 57,200 divided by the change in entropy in joules minus 175 means that the temperature at which the reaction will become non-spontaneous or will flip over is 325 Kelvin. Now be careful. I don't usually do this on purpose, but a lot of the standardized questions will ask you, well, what is the temperature in Celsius? Remember that when you use this equation, the temperature you get is Kelvin, and the temperature you must use is Kelvin. So if it asks in Celsius, you're going to have to do another conversion. Just to remind you that degrees Celsius is Kelvin minus 273. Some of you are used to seeing the equation written in terms of Kelvin. So if we rearrange that equation, Kelvin equals degrees Celsius plus 273. The bottom line here is to remember that the Kelvin value of temperature will always be higher. Okay, so 325 Kelvin So we have actually got to subtract 273 from Kelvin to get Celsius. I just realized this is wrong. So what do we get here? 52 degrees Celsius. I have no idea how I got, I think I added. Okay, so again, this little tidbit, Kelvin always needs to be a higher value, will help you make sure you do the right thing when you convert it. So in order to do this particular reaction, what are they talking about? Delta S, delta H, delta G, and didn't they give it to us? Isn't this that? No. Okay, so this is almost a whole lecture in itself. I should probably add a few more slides. it's not hard, but it's just another level of something you need to know. So we have our equation that tells us delta G standard equals delta H standard minus T delta S. Now these are all for the reaction. So change in free energy for the reaction, change in enthalpy for the reaction, change in entropy for the reaction. Notice the delta H and S given up here are formation, okay? And this is not delta S, it's just S. So what's going on here? All right, so this is something you were supposed to cover in 1211, but I'm going to kind of go over it again. It turns out these little F mean formation. And so there's an equation that says delta H of a reaction, the change in enthalpy for a reaction, equals the sum of what we call heat of formation for the products minus sum of heat of formation for the reactants. Okay, products minus reactants. So in other words, this problem wants you to calculate delta H of reaction first and also calculate delta S of reaction first. Using these values, there's a similar. So delta S of reaction is sum of enthalpy of products minus sum entropy of reactants. All right. And once you have calculated both of these values, you can then use delta G equals delta H minus T delta S. Alrighty. So here's the formula to calculate delta H of reaction. And let's go ahead and write what we would have here. Heat of formation, or enthalpy of formation for products. What are our products? SO3. Okay, so first of all, you have to take coefficients into account. So we have 2 times the heat of formation for SO3, which is minus 396. That's in kilojoules, okay? Pay attention to units. That's the only product, okay? Now, minus the sum of heat of formation of the reactants. We have 2 reactants. So enthalpy of formation for SO2 is minus 296.8 kilojoules again. Now, one important thing to remember, and you may from first semester chemistry, but the heat of formation for elements in their standard state, which means how they exist in nature, and oxygen in nature, first of all, is diatomic, exists at O2, and if you look back, it is in gas form, which it is in nature. So the heat of formation of any element in its standard state is 0, okay? Oops, it's plus. All right, so if you go ahead and do this calculation, let's see what we get. All right, be careful with your signs. All right, so then my final answer is going to be minus 792 plus 593.6. And I get that delta H of reaction is minus 198.4 kilojoules, which means this is an exothermic, favorable from a point of view of thermal energy. Now let's figure out what delta S for the reaction is, okay? Products minus reactants. Alrighty, so products minus reactants, so Products are SO3 again, so 2 times, if you look back at the table on the last slide, the entropy value for sulfur trioxide is 256.66. It is joules. Beware of that, okay? Not kilojoules. Again, that's the only product. So now we're going to do reactants. Okay. Let's look at the value entropy for sulfur dioxide. And it is 248.1. Again, joules. Okay. Now, entropy, there's nothing in our universe except a crystal at 0 Kelvin, which has 0 entropy. In other words, everything has entropy. So even though delta H and delta G can equal 0 under certain conditions, delta S will never equal 0. All right, so the entropy for oxygen is 205. Again, it's in units of joule. So go ahead then and calculate the entropy change for the reaction. All right, so for the first part of that, 2 times 256.66, that is 513.32 joules, minus, let's do inside the brackets first, so 2 times 248.1, whoops, All right, so that part of it is 496.2, and then we're going to add the 205 onto that. All right, so the enthalpy change for this reaction is let me do this first. That is 701.2. All right. So it's going to be negative. That's unfavorable. So let's see, plus 513.32. So delta S for this reaction is minus 187.88 joules. I'm going to go ahead and change that to kilojoules right now so that it matches the units for the enthalpy. So I'm going to divide by 1,000. So it's minus 0.18788 kilojoules. Now that you have delta H and delta S, you can plug them in back into the equation for delta G. Alrighty. All right, we're trying to find delta G now. And so what is the value we got for delta H? It is minus 198.4 kilojoules. Temperature, what is temperature? Remember, it has to be in Kelvin. Okay, the problem gave us 45 degrees Celsius. So the Kelvin value is 318. 318 Kelvin times the value we got for change in entropy. Okay, and put it in kilojoules and just rounded it a little bit. All right, let's go ahead and calculate and see what we have here. I'm going to do this first. All right, so that is, I think I punched that in wrong. Hold on. Here we go. Minus 59.8. Okay. All right, the two negatives are going to give you a positive, right? So we've got minus 198.4 plus 59.8. And so the final delta G value minus 138.6 kilojoules. That is a spontaneous process. It's negative. Okay. So it takes a lot of practice to do these. So the more problems you can do, worded all different ways, the better off you're going to be in succeeding to do these. That's it for this PowerPoint.